There we go. All right, we get started. So I'm Wenming again, and welcome to the August DGL or GNN user group meeting. So our community has been expanding quite a bit, and I just noticed that we have almost 1,400 people in our Slack channel, and actually expanding more. I was just visiting UBC. And UBC is University of British Columbia in Canada. It's very close to Seattle, so I live in Seattle, and went up there, and there was a group of 45 graduate students, and I asked them who knows about DGL. It turns out that at least 1/3 of them, I think it may be 1/4, I would say 1/4, one of them actually knew about DGL. So graph is a very popular topic, and you can think of it, this is a group of computer science students, graduate students. So the fact that 1/4 of them have some interactions with graph, so this is a really growing field. So we're very excited to I was very excited to see that. So any other news folks want to share other than what Joe just shared with us? And so if you want to go to this year, if you want to go to GTC, is it virtual or is it in person, Joe?
It'll be virtual this year, yeah, for the fall. Hopefully the spring will be in person.
Okay, so let me maybe put up a link for that. So GTC in September. So it's September 19th to, so let me just put that into the link here. So September, let's see, 19th to the 22nd. And Joe is going to talk about, so you're going to keynote, or is that going to be?
No, I'm in charge of the GNN talks. So Da Zhang is giving a talk. I'm going to give a talk. We've got another talk on general data science applications with Rapids, stuff like that. Yeah.
Oh, that's perfect. So let's just get started on the first talk. So we have Yiyue here, so she's already online. Thank you so much for taking the time to talk to us. And I assume that school is going to start very soon for you.
Yeah,
again.
Sure.
Great.
Can I share my screen?
Yeah, so you can share your screen. And so she's going to talk to us about Rep2Vec, a repository of embedding via heterogeneous graph adversary contrastive learning. So yeah, that actually worked. That sharing did work. You have to share it again. Yeah.
Can you see my my slides?
Yeah, we can see it now. All right.
Okay, you can see my slides, right?
Yeah, I'll let you introduce yourself.
Yeah. I will first introduce myself. My name is Yiyue Qian. A fourth-year PhD student at University of Notre Dame, and this year I was a scientist intern at Amazon. This summer, and this work I'm gonna introduce is accepted by the KTP conference this year. Yeah, and okay, next I will go start. The topic I'm going to talk about today is to build a repository embedding model via repository to vector via the heterogeneous graph adversarial contrastive learning. This is the honor of the work, and I will briefly introduce the background. With the increase of software and the advent of the pool-based development system, Git. So more and more open source software have emerged on social coding platforms such as GitHub. So this is the figure, and figure 1 shows some content information of a repository, including the owner, the project title, the description, the topics of the repositories, as well as the source code and the relation forking and storing. So except for the rich text content, the relations among social coding platforms such as GitHub is also very rich. So in this topic, we are gonna build a self-supervised model using the unlabeled data repository to vector, and then the model can be fine-tuned to the downstream tasks such as the malware detection, the repository link prediction, and also the repository topic prediction. Next, I'm gonna briefly discuss some challenges of this work. First, most existing works always focus on the code content, but ignore the rich relational information on social coding platform. In addition, most of them require a lot of resources to obtain the sufficient label data, while ignoring the unlabeled and handy unlabeled information. In addition, for different applications, existing work needs to develop different models, which is time-consuming and energy-consuming. So to solve the first challenge, we build a heterogeneous graph to describe both the code content and the rich relation among the repositories. And then we further apply the geo models to encode the repository. In addition, to handle the second challenge, we develop a self-supervised model, self-supervised constructive learning model to pre-train the geo encoder with unlabeled data. And then the pre-trained repository model can be fine-tuned to most repository applications, such as the repository classification. Before introducing the problem definition of this work, I'm gonna briefly introduce what's the graph contrastive learning, and I provided some important related works about graph contrastive learning. The first one is the GCC. The first one is the GraphCL, and the second one is the GCC. The third one is the HECO, and the last one is the ADGCL. The first one, the first work, the second work, and the last work, they focus on homogeneous graph, and the first one, the third one, focus on the heterogeneous graph. I will briefly introduce one of the work, then we can have a sense about graph contrastive learning. So this figure shows the framework of graph contrastive learning. GraphCL defines four groups of graph data augmentation, like the node dropping, age perturbation, attribute masking, and the subgraph. So in this figure for the input graph G, so the GraphCL will sample two data augmentation from the data augmentation pool, and then the augmented graph will be applied to the input graph G, and then the graph will be fed to the geo encoder and followed by a projection head. So in this figure, if I equals J, then we can consider them as a positive pair. Otherwise, I doesn't equal J, then they will be considered as a negative pair. So the purpose of the graph contrast learning is to maximize the agreement with between the representations Ji and Jj while contrasting loss. Next, I'm gonna briefly introduce the problem of this work. Given a heterogeneous graph G of the repository data, we aim to build a machine learning model to learn the repository embedding with unlabeled data that can be fine-tuned or applied to downstream applications, such as malicious repository detection and also the repository link prediction. This is a framework of repository to vector, which has 3 steps. The first one is the repository heterogeneous graph construction. The second step is the dual string graph contrast learning. And the last part is the model fine-tuning on the downstream task. And I will briefly introduce the heterogeneous graph construction. the figure 3 here is the network schema for repository heterogeneous graph, which has 3 types of entities and 4 types of relations. So from the table 2, we listed each type of node and their text content, as well as the rich relationships. I will give some examples to describe them in detail. So here for each repository, we not only consider the metadata, such as the title, description, readme file, as well as the source code, such as the C, C++, script, Java, Python, and so on. And then we also define 4 types of relationships, R1 for R4, and the to semantically describe the relationships among the repositories and the users, as well as the topics. Then we define 3 metapaths to describe the semantic relationship. So I will give 2 examples: the metapath, the first metapath, and the second metapath. The first metapath describe that the repository is forked by the 2 repositories are forked by the same user, and the second metapath shows that the 2 repositories are started by the same user. So to conclude, in this work, we have 3 types of entities: repository, user, and topic, 4 types of relationships, as well as 3 metapaths. After graph construction and feature extraction, we all know that for different node types, they have different the feature vector have different dimensions. So in this way, we first need to transform all of the node features to the same space based on the equation 2. So we transfer all of the node features to with the same dimension, and after feature transformation, then we perform the PGD attack to the node feature, and then we will get the adversarial graph detailed. So from figure 3, after getting the adversarial graph, then we will feed the adversarial graph to the Qian encoder and further get the node embedding. Here for the Qian encoder, we use the 2-layer GCN as the Qian encoder. So after that, we need to perform the graph contrast learning. Now in this work, unlike most existing works that only consider 1 positive pair for each node. So here we consider the multiple positive pairs for each node. Specifically in figure in equation 5, for each node vi in V, you will have like 2 node sets, VIL and VIS, having the k largest similarities and the k smallest similarities with respect to the attribute features. And then if the embedding, so if the embedding Ij and Ij, they will be considered as a positive pair if they as a positive pair if J is in the VIL, which means that we assume that the embeddings of node pairs, they should have similar embeddings if their attribute features are close. So otherwise, if their attribute features are away, then we think their embeddings should be away. So if J is in the VIS, then they can be considered as a negative pairs in contrast learning. So The equation 5 is the adversarial string contrast learning under the node view. Next, I'm gonna introduce the MetaPath view graph contrast learning. As we mentioned that the node view contrast learning can balance the importance of the attribute features as well as the structure relationships. However, it cannot describe the high semantic relationships among nodes. We all know that the MetaPath can depict the heterogeneous relationships among nodes. So in this work, we define 3 MetaPaths to describe the heterogeneous semantic relationships among nodes, and for each subgraph, we will also perform the PGD attack, and then we will get the adversarial subgraph, and also for each subgraph, we will feed the the graph to the geoencoder, and then we will get the node embedding for each node. So this is the MetaPath view contrast learning based on the equation 6. If H, the equation 6, HIPL and the HJPM, they can be considered as a similar pair, or we can say positive pair if I equals J but L doesn't equal M, which means that the embeddings of the same node, on the different MetaPaths, they should be similar. Otherwise, if I doesn't equal K and L doesn't equal M, which means that the embeddings of different nodes on the different MetaPaths, they should be away. So so the equation 6 is the adversarial string contrast learning loss under the MetaPath view. Then I'm gonna conclude the adversarial string contrast learning loss, which has 2 terms. The first item is the node is the adversarial string contrast learning on the node view, and the second item is the adversarial contrast learning under the MetaPath view. Then after that, in consideration of the adversarial attack to the whole graph and each subgraph will be too challenging and stressful for the geoencoder. So here we also perform the graph contrast learning on the original graph. So the process should be the same except the PGD attack. So the black line shows the original string graph contrast learning. Also, the original string contrast learning has 2 items similar to the adversarial string contrast learning. To conclude, our model do-string contrast learning has 2 items. The loss have 2 items. The first one is the adversarial loss on the adversarial string contrast loss under both node view and the MetaPath view, and the second item is the original string graph contrast loss under both node view and then the MetaPath view. So that's the main frame of the model. And then after pre-training, after finishing the pre-training model, then we introduce the knowledge distillation technique to distill the knowledge from the pre-trained model, or we can say the teacher model, the unlabeled information, or we can say AKA like a softer knowledge. And then the softer knowledge will be transferred to the student model. So as we can see here in here for the equation 10, the phi t and the phi s are the distance-wise the relation function on the teacher model and the student model, and the LH is the Huber loss that penalize the differences between the teacher model and the student model. So after that, the student model will be fine-tuned with the non-distillation loss as well as the task-specific loss. I will give an example like the malicious repository detection task. Then the task-specific loss should be the cross-entropy loss. After introducing the model, the methodology part, then I will briefly introduce the experiment and the analysis. The dataset we use is crawled from the GitHub from August 2020 to August 2021. To conclude, the constructed heterogeneous graph has more than 100,000 nodes, as well as almost 900,000 edges. In this work, we have two downstream tasks. The first one is the malicious repository detection task. So for this task, we obtain almost 24,000 repositories, including more than 3,000 malicious and also more than 6,000 benign repositories. For the second task, the repository link prediction, or we can say the repository recommendation, we obtain over 100,000 forking links and almost 500,000 downstream links as the ground truth for the repository link prediction task. We need to mention that for the first task, the malicious repository detection task, we first implement the virus total, having over 70 anti-malware scanning tools to validate the legitimacy of a repository. In addition, we then ask anti-malware experts to confirm the legitimacy of a repository. Next, I will briefly introduce the experiments with baseline models and our model on malicious repository detection task. So we have four groups of baseline models: G1, G2, G3, G4, and our model repository to vector. G1 are models with traditional repository features, and the G2 are 6 graph models. G3 are 3 existing models against the malicious repositories, and the G4 are 3 graph contrastive learning models. So by comparing with G1, G2, and G3, we can find that the rich relationships among entities can improve the model performance. Only considering the code content is not supported enough to detect the malicious repository. In addition, the graph model designed for heterogeneous graphs like the RGC and the Han outperform the homogeneous graph model like the GCL and GAT, which shows the effectiveness of the heterogeneity for detecting the malicious repository. In addition, by comparing with G2 and G4, we can conclude that the unlabeled data contributes greatly when we use unlabeled data to pre-train an encoder for the repository embedding. And after by comparing with all of the baseline models, the repository to vector is proved to have the best performance on this task. In addition, I will introduce the experiments on the link prediction task, the repository link prediction, or we can say repository recommendation. We have 3 baseline models, and our model we will get almost the same conclusion as the previous task. First, the rich relationships among entities increase the model performance by comparing with C1 and C2. In addition, features are also very important to improve the model performance, as the performance of graph model without feature like a node to vector and a metapath to vector are much worse than the graph models with features like VGAE, GAT. So in addition, the models in C3 outperform the VGAE in C2, although VGAE and models is in C3 use the same Qian encoder, which validate the unlabeled data contributes greatly for link prediction tasks. To conclude, the repository to vector, the model has the best performance on the repository link prediction task. Then we conduct the application study to evaluate the effectiveness of each component in repository to vector. So from the figure 7, we can conclude the downstream contrast learning has the biggest contribution to repository to vector, as the performance of A1 drops very obviously on both tasks. In addition, the performance of removing adversarial attack on both datasets decrease obviously and also shows the effectiveness of adversarial attack in repository to vector. In addition, we can also find the A3, A4, like a fine-tuning process and the knowledge distillation module have a contribution to the repository to vector. Next, we also compare the repository to vector with some commercial products. The table 4 shows 5 commercial products and one product provided by GitHub. We can conclude that the repository to vector achieve at least a 2% improvement in accuracy and F1 by comparing with the base commercial products in table 4. In addition, by comparing repository to vector with LGTM provided by GitHub, repository also gains over 20% improvement in accuracy and F1. Last, we also visualize the embedding, the repository embedding generated by our model and the 3 baseline models. We can see that the repository to vector generates the most distinct boundaries and the smallest overlapping area between the malicious and the benign repositories. Next, I'm gonna briefly conclude the contribution of this work. So we developed a novel model called repository to vector, which comprehensively integrates the code containing information, the structural relation, and the handy unlabeled data on GitHub. In addition, to the best of our knowledge, repository to vector is the first work to propose downstream contrast learning on heterogeneous graph, which integrates the contrast learning with 2 views on the adversarial graph as well as the original graph. In addition, we collect a new dataset from the GitHub and conduct a comprehensive experiments on 2 downstream tasks to evaluate the effectiveness of our model. This work is partially supported by the NSF funding, and well, that's all I wanna share with you guys. If you guys have any questions, you can ask me questions. You can feel free to ask questions, and yeah. Did anybody have any
questions? I think there was an earlier question asking you to explain more about the node views. For some reason, it was directly sent to me. So Yeah, so that was
yeah.
that was a question.
Okay, yeah. Okay, I will share my screen. Hold on a second, and then I can explain.
Can I talk?
Yes, please. Yeah, you can. Yeah.
Yeah, this is Mahmoud. Actually, I'm working in cybersecurity, real application industry. So when you are talking about node view or multi-view, sometimes I'm seeing multi-view contrastive learning. So what is the meaning of this?
What's the meaning of the multi-view contrastive learning? Right.
Yep.
Okay.
Yep.
So yeah. Okay. So for node,
you had two different boxes. One was for node view, another was for metapath view.
The metapath view. So the node view, is the node view contrastive learning is to balance the importance, or we can say the importance of the attribute features as well as the structure relation. We know some work they prove that the most GL models, they are dominated by the structure relation among nodes. So that's why I wanna use the node view contrast learning to balance the effectiveness of node feature and structure relation. So that's the node view.
Okay, what is the other works than working with attention networks? You know what? We are in vulnerability, for example. So we are one of the things to just deal with false negatives and true positives is doing ranking and get most severe vulnerabilities or malwares without dealing with or analyzing the TFN. If I mean false negative. So what I'm trying to say is, do we need to deal with attention networks here or no? For this feature importance when you're talking.
I beg your pardon. So do we need to use what?
I'm trying to say how you are finding this feature importance. Each feature after applying different methods going to generate weight and a score.
Okay.
So
yeah. So you mean what kind of features are important, right? For to represent a repository.
Yes.
So that's what you want to ask, right? Okay.
Yeah.
So okay. So for the repository, so we consider the metadata and the source code. We consider them as the test content. So we do not have any like numerical features. All of the features here are the text feature. So we consider all of the text feature of the repository, or for user node, we consider all of the text for user, right? Okay, so for this one, we will combine all of the text features, and then we will feed them to a pre-trained model like a BERT or distill BERT to get the embedding.
Okay.
Yeah.
Okay, so what is the difference? Sorry, I'm interrupting others. I just want to understand something, at least for myself, and probably other people can use. The thing is, we have graph, we have some software metrics just to find those bugs or vulnerability or malwares from there. These dependencies, for example, one node in the graph has more dependencies. Probably the number of vulnerability for this graph is going to be using, for example, code complexity, number of line of code for each function. We have two different vulnerabilities, for example, or malware, function level and file level, which is most of the time now, all the papers focusing on function level. What I'm trying to say is, if we could add some statistical things, just like statistical metrics of software in this type of data set, it is going to be very strong in the detection.
Gotcha.
So I don't know if someone had the similar experience.
We do not like so we do not we haven't like selected the features. So you mean maybe some features are important than others. So that's what you mean?
But you said we don't have in this project any numerical features.
Yeah, we don't have any numerical features. So all of features are text content, and then we feed them to the pre-trained language model like a distillable. Yeah.
Okay. All right. Yeah. Thank you so much. Thank you.
Yeah. I can explain more on node view contrast learning if you are interested. Yeah.
This is actually a good presentation that I got some idea to just continue on this. Thank you.
Yeah, we can talk more after that.
Thank you.
Is there anyone have any questions? If not, yeah, then.
I think there's one in the chat.
Hold on. One is in the chat. Okay.
Yeah, there's one in chat. You can look at it, and if
what's that?
So Ita, if you want to maybe unmute yourself and ask the question yourself, that also is fine.
What's up? Hold on. I think I need to stop sharing her first.
Yeah, you can stop share.
Okay. I can stop sharing. Okay.
Yeah, you'll see it. Yeah.
What are any other relational entity? I think there are many relations in that domain. Okay. Mainly the behavior that is hard them to sound choice. Honestly, we have like some papers in this field like to detect malicious repository, right? In other works, we also consider like other entities like the file type, like the file type, such as the exe file type, the executable file, and also the py file. Yeah, and also for the relations, they are also some other relations, except these four, like we can also have something like okay, if the repository belongs to if some of the file in the repository like the file type of the file type in the repository belongs to another file type. So this should also be can be considered as a one relation, and the file type can also be considered as a entity. Yeah. So are you clear with that? Oh, you can. Yeah.
Yeah. Can you hear me?
Yeah, I can hear you.
Okay. I have a question. One more. Is there any others node features or link features at there?
You mean the picture, right? Picture on GitHub. We do not consider the image like a feature model, but we can do. It's not a big deal. We can consider the image, and then we put the image to the relational model, and then the image like embedding can be concatenated. The image embedding and the text embedding can be concatenated to a feature vector. So yeah, like the multimodal. Yeah, it looks at the multimodal feature.
Okay, thank you.
Yeah, thank you.
Hi.
One more question. You can go first. Sorry.
But Joanne, you can go first, I guess.
Oh, okay.
Let me.
You
can go first.
Yes, thank you. This is very good presentation, but I was late, so I saw the metric, the loss function has something like a similarity, looks like a clustering. So then, but this the goal is like sounds like a binary classification. So I don't know how how this what is this constructive learning, because it looks like it seems to detect the malicious repository. But I saw in the loss function, it's like clustering. It's like similar, not similar, you know. So
I can get your point. Yeah, so you're talking about the fine-tuning loss, right? The fine-tuning loss. Okay, I can share my screen again. Hold on a second. Do you mean this side? This one?
Oh yes,
this one, right? This one. For simply fine-tuning, right? So we do not use the knowledge distillation technique. So we can just fine-tune the pre-trained model with the cross entropy loss, because most of our tasks, they are binary classification. Like for the malicious repository, right? The binary, and for the link prediction, we predict whether there is an age among two nodes. However, we introduced the knowledge distillation technique to transfer or to distill the unlabeled information from the pre-trained model. So what is the pre-trained model? The pre-trained model is this model. So this model, this dual-string graph contrast learning model, are trained on all of the unlabeled data. It doesn't consider any label data. So we assume that they use a lot of unlabeled data. So it should have some knowledge that can be learned to the student, that can be learned by the student model. So that's why we use the knowledge distillation. Like we distill some software knowledge from the teacher model, and then we transfer the software knowledge to the student model. So the student model has two loss to optimize the model. The first one is the cost entropy loss, right? The task specific loss, the cost entropy loss, and the second loss is the KD loss. So what's the KD loss? The KD loss is to how do you say that? Is to penalize the differences among the teacher model and the student model. The Huber loss is to penalize the differences between teacher model and the student model, and the phi t and the phi. Phi t is the distance, a distance-wise function to describe all of the data, data in the teacher model. Yeah. And also the phi z is the relation function on the student model. The knowledge distillation loss, he asked the how do you say that? He aims to let the student model to learn the self-knowledge from the teacher model. So that's the purpose of the knowledge distillation module.
So you said it is mostly is unsupervised, so there's not labeled.
This one, the teacher model is trained on labeled data. This teacher model is this model, and is already pre-trained.
Trained on labeled data.
Okay. The teacher model, right? The teacher model is complete right now at this stage. It's complete at this stage. So what's the teacher model? The teacher model is this part. So it's already pre-trained with the contrastive loss. The contrastive loss, yeah.
Is it like what's the teacher model? What is the label? I mean, what is the
label for the teacher model, right?
Yeah. Is it
it's a pseudo label. It's a pseudo label for each node. It's a pseudo label. So that's so what's the pseudo label? So for node view, it has for each node it has a pseudo label. Okay, if for each node bi, right? So it has two node sets. The four node sets is the VIL, that having the k largest similarity with respect to the attribute features. So that means, okay, if the node J has the similar that has the similar attribute feature, then we think their embedding should also be similar. And then this node pair can be considered as a positive pair, or as a positive pair in contrast learning, in node view contrast learning. Yeah. So that's the pseudo label. Like these two nodes, they are a pair. They are a positive pair. So that's the pseudo label.
Oh, yeah. Anyway, so is there a paper so I can read?
Yeah, sure. The paper is accepted by the KDD conference this year. Yeah.
Oh,
I can.
Because you just a quick question. I heard you mention the link prediction. So
yeah.
why? So this model is to do multiple tasks, to do the. Oh.
Is to do multiple tasks. So the purpose of this. Okay, hold on. The purpose of this work is to build a self-supervised model repository to vector with all of the unlabeled data. So this is the pre-trained model. Then the pre-trained model can be fine-tuned with downstream tasks with like the label, downstream task label for different like applications, like the malware detection and then the link prediction, or we can say repository recommendation, yeah, something like that.
Oh, I see. Oh, that's great. Yeah. So did you share your paper name?
Yeah, sure. Yeah, this is and I will also send the paper name to the chat.
Yeah, you can also put it on the Slack channel as well. Yeah, that would be good.
Yeah.
Well, thank you, Yiyue. I think that's all the time we have.
Yeah. Thank you for inviting me.
Of course.
Yeah.
And next we have Chunxing Ying from Georgia Tech, and she's going to talk to us about Nimble GNN embedding with Tensor-Train decomposition. So, and Chunxing, you have the floor there.
Thank you. Hi, everyone. I'm Chunxing Ying from Georgia Tech. And let me share my screen really quick. So. Sorry, the screen sharing is not working. Okay, now it works.
Yeah, it should be enabled. Yeah, take your time.
Right.
No worries.
I cannot see like which one I'm sharing.
Yeah, that's right.
Like all blank screen, so I'm kind of confused here. Okay. Oh. Can you see my screen now?
Not yet.
Oh.
Did you log in as yourself, or?
Yeah.
I can maybe make you a co-presenter of some sort, but that might work.
No, I think that's my laptop's problem. It's not.
Oh, okay. Oh, yeah. Now
Does it work now?
Yeah, it's working now.
Okay, great.
You can see it.
Okay, so yeah. So today I would like to present our work Nimble GNN embedding with Tensor-Train decomposition. And most of this work was done during my internship last year in the digital team. And here's a brief outline. I will go through the definition of GNN and Tensor-Train decomposition, which is the used for our embedding representation in this work. And I will talk about the methods we propose to improve the accuracy of our model, and then selectively go through some of our results. So on a high level, the motivation of this work is to learn node features for massive featureless graphs. And the reason is that when we apply GNNs on real-world problems, we often encounter graphs with billions of nodes and edges. For example, Google's knowledge graph has over 500 billion facts spanning over 5 billion entities. And a significant scaling challenge occurs when the graph does not come with explicit or high quality node features. And in this case, what we usually do is to associate a trainable embedding vector with each node. And this trainable node embedding becomes part of the overall model parameters. And that requires terabytes of memory for a graph with billions of nodes. And clearly, this memory requirement exceeds the capacity of all our modern GPUs. And the general practice is to keep them on the CPU and only do the computation in GPU. And it was observed by a lot of existing work that this data transfer between CPU and GPU, as well as the parameter updating in CPU, becomes the becomes the major performance bottleneck during massive GNN training. And therefore, in this work, we explore a new method for representing embedding tables in GNNs more compactly using Tensor-Train decomposition. And in this plot on the right side is a summary of our findings on the OGB node property prediction tasks. So we plot the test accuracy of our model, and the full embedding model serves as a baseline, and the training time of each model. So the size of each data point in this plot is proportional to the number of parameters in each model. And looking at the smaller data sets, our models were able to outperform the full embedding model using more than 400 times fewer parameters. However, the training of our model is slower. But things become different when we move to this 100 million node graph, where we use at least 1,600 times fewer parameters, and the training of our model is up to 20 times faster than the full embedding model. And so for the background, I guess a lot of audience here is very familiar to GNNs, so I'll just go do a very brief introduction. And on a high level, like most of the GNNs can be summarized using this message passing framework, where each node aggregates the messages received from its neighboring nodes and to form its own node embedding at its current layer. And for example, if we start with this green node, in the first layer GNN, it will aggregate the embeddings from all the yellow nodes, and next layer, all the yellow nodes will do the same thing to aggregate the node embedding from their neighbors. And the input to this network is the node feature, the floating point vector associated with each node. And in our work, we only focus on providing a more compact way of storing the node embedding to serve as the input to the GNNs. And next, let me introduce the Tensor-Train decomposition. So this is a method introduced in 2011, and it describes a way to factorize a d-dimensional tensor using d small tensors, each of 3-dimensional. For example, here, if we have this 4-dimensional tensor A, it can be factorized using 4 small tensors, and each of the small tensor is called a TT core of shape R of k minus 1 by ik by rk. And ik here is the cardinality of the kth dimension of the tensor A. And the sequence rk is the most important factor in this tensor train decomposition. It's a user-defined parameter called TT rank. And it can in fact affect both the accuracy of this decomposition and the size of the decomposition. So overall, by using a large TT rank, we would have more accurate approximation to the original tensor, but that at the cost of using more parameters and more computation for reconstructing the tensor. And to reconstruct one element of the tensor A, we multiply the corresponding slices from each TT core. And this definition can be generalized to matrix decomposition, but here we don't want to directly apply the previous definition. Otherwise, it will turn into an equivalent thing as matrix factorization. So to achieve better compression, we first fold and reshape a matrix to a large dimension tensor. For example, it can be 8 modes or 10 modes. And what we do is to say here we can cut a matrix 4 ways and fold it to form a 4-dimensional tensor, and then repeatedly cut each slice and fold it to form a high-dimensional tensor. And so to compare to and to visualize how things change between a regular tensor train decomposition and the tensor train matrix format, previously we used 3D TT cores to decompose the matrix, and now we kind of extend the index from in each TT core to include both the row and column index. So for the matrix decomposition, each TT core gonna be 4-dimensional. And to compute for an entire row by tensor train decomposition, we can formulate the computation as 2 consecutive matrix multiplications by multiplying the unfolding matrices of the corresponding subtensors in each TT core. And I will be using 3 TT cores as demonstration in this work, but this can be extended to using arbitrary number of TT cores. By using more TT cores, we will potentially have fewer parameters, but we will have more computation when we want to reconstruct the matrix. So the chain of the matrix multiplication here gonna be longer. And to use the tensor train decomposition as a trainable module in the GNNs, we just replace the original embedding matrix with its tensor train format and randomly initialize the TT core weights. In the forward propagation, we reconstruct the embedding vectors from the TT cores, and in backward propagation, we compute the gradients with for each TT core and update the weights. And in our work, we propose 2 ways to improve the training accuracy of our model. And the first one is graph partition. So the motivation here is that in many real-world graphs, they are homophilic, meaning that nodes share the same label as its neighbors. And therefore, we want the embedding to reflect this property as well. So the topologically closer nodes should have a similar representation, and therefore they will be more likely to be categorized as the same type of nodes in the node property prediction tasks. So we propose to reorder the nodes based on the hierarchical graph partition. And let me explain this with a small example here. So we have this graph, and we do a three-way partition of the entire graph, and we will relabel the nodes inside each partition consecutively. This will ensure that during the embedding reconstruction, all the nodes inside the same circle will share the same slice from the first TT core. And if we recursively partition each of the orange area and relabel all the nodes inside each green partition, we can ensure that all the nodes in each green circle share the same weights from the second TT core, and so on and so forth. So as we can see here, that ordering the nodes based on the graph topology would better promote the weight sharing among topologically neighboring nodes, and therefore our Tensor-Train embedding can produce a homophilic representation after this node reordering. And the second method we used in this work is orthogonal initialization for the TT cores. It is well understood that orthogonal initialization for the networks can accelerate convergence, and therefore we want to initialize the TT cores in such way so that when we reconstruct the entire embedding matrix, the embedding matrix W would be semi-orthogonal. And one way to do this is very intuitive. We can just randomly generate a large orthogonal matrix W and decompose it using a SVD-based method to get the weights for the TT cores. However, there's a problem with this method, is that during this process, it involves computing the SVD of very large matrix, say when we have a graph with 100 million nodes. And therefore, we offer an alternative approach where we directly initialize the subtensors of the TT cores in a specific order, and each subtensor can be directly set from a small orthogonal matrix. So to compare those two methods, for algorithm 1, it is scalable to arbitrarily large TT ranks. However, it can be inefficient for large graphs. And for algorithm 2, it is very efficient. It only takes a few seconds for a say 100 million nodes graph, and it guarantees the orthogonality of the embedding matrix W as well as the unfolding matrices of each TT core. However, this algorithm is only applicable to relatively small TT ranks, and the reason is that during this process, we generate this each time we want to generate the orthogonal vectors of length mi times ri, and that means we can generate at most mi times ri number of vectors that are orthogonal to each other. So this puts some constraint on the factor of the matrix dimensions. And we studied the performance of our proposed method on 3 node property prediction tasks. And the first 2 data sets are smaller, so the full embedding table can be stored on GPU. And the third one, we keep the full embedding on the CPU and update the full embedding weights on CPU. So here is a summary of the accuracy and training time, as well as the memory consumption of our models and the baseline. And the table on the top is for the 2 smaller data sets. And we would like to point out that our model achieves higher accuracy with using more than 100 times fewer parameters. And our model is slower because we introduce extra computation into the training process to reconstruct the embedding vectors during the forward propagation. And we compared the performance of our model to the full embedding model. And in this process, so for the full embedding and our model, we only use one hard encoding for each node. We didn't use the original node feature provided by the dataset. However, we did compare the accuracy to the model that's trained with the original features. The original features, typically they're like pre-processed, pre-computed vectors based on the like text information associated with each node. And we found that on the products graph, the quality of our trainable embedding is actually comparable to the original node features. And remember that in our work, we only train the model based on the graph topology alone. And for the large data sets, the papers 100M, we outperformed the full embedding even with a very small TT rank after applying graph partition and orthogonal initialization. And here we can see that the compression ratio of our model can be as high as 81,000 times. I know this looks crazy, but we think this is a dataset related issue where we observe that graph partition is extremely effective on this one dataset. But more generally speaking, in other datasets, we usually achieve around like a few hundreds to 1,000 times compression compared to the full embedding. And for this large dataset, by using our model, we can fit the entire model on GPU, and therefore the training of the TT embedding models are much faster than the full embedding. And I will show why that happens in the next slide. So here is a time breakdown of the single GPU training of the full embedding and the TT embedding on the papers 100M dataset. And we plot the time spent in each kernel during the training. We break them to forward propagation, backward propagation, and parameter update. As we can see here that the full embedded model was kept on CPU, and every time we copy the current embedding rows from CPU to GPU for mini batch training. And after the gradient calculation, the GPU sends the gradients back to the CPU to update the weights. And therefore, we observed that most of the time was actually spent on parameter updates on the CPU for the full embedding model. And we also studied the scalability of our model on multi-GPU training. And we benchmark the performance of our model on two different AWS instances using different GPUs. And those are represented by different, the two different colors in this plot. And within each color group, the darker shades correspond to model configuration with larger TT ranks. So overall, we see that when we use larger TT ranks, the TT embedding part will dominate the training time, and therefore the multi-GPU distribution achieves a nearly linear speedup for those models. And next, I want to briefly talk about the effectiveness of our two proposed methods. So the first is graph partition. In this plot, what we show is the number of how number of partitions affect the test accuracy of the graph stage model trained with the products graph. We first observed that by using even a very small number of partitions is beneficial to the model training. It improves the accuracy of graph stage by roughly 7%. However, as we keep increasing the number of partitions, we see that a overly fine-grained graph partition is unnecessary because the TT embedding is actually robust to the bottom level node permutation within the hierarchical graph partition. So please see our paper for more detailed analysis on the robustness of TT embedding, with the metis partition. And here I want to talk about the how the initialization works. In this plot, the 3 color columns are models trained with a model only differ by initialization algorithm. And we plot the accuracy of the models trained with different TT rank and different number of partitions when we pre-process the graph. As we can see here, that compared to initializing the TT embedding from Gaussian distribution, the 2 orthogonal initialization algorithms improve the test accuracy in a similar way across all the configurations and models. And as I mentioned before, that algorithm 1, which is decomposing a large matrix to initialize the TT cores, it is scalable to large TT ranks here, 32. And however it is slower, it will take about half an hour for the paper's 100M on the CPU instance with about 700 gigabytes RAM. And 1/4 of the time will be spent on generating the large orthogonal matrix of size 100 million by 128 using QR decomposition. But by contrast, algorithm 2 only takes a few seconds to initialize the TT cores of the same shape. So as a summary, in this work, we explored using Tensor-Train decomposition as an alternative compact parameterization of node embeddings in GNNs. And we showed that by using orthogonal initialization to the TT cores and reordering the nodes based on hierarchical graph partition can largely improve the accuracy of our model. And on all the 3 node property prediction tasks, we achieved a significant compression ratio while improved the accuracy compared to the full embedding model. And that's all my presentation today, and I'm happy to take any questions.
Hey, thanks for a wonderful presentation. This is Vikram here. I have read your previous paper, TTREC, and that's also a very good paper too. But I'm one of the things that I'm still unclear from this work is why should we see a better accuracy when we do the tensor decomposition? I think I understood on the later part, it's not from the tensor decomposition, it's mainly because of graph partitioning. And since you are doing the graph partitioning, it's actually increasing the accuracy better.
Yes,
but do you
that's correct.
Okay, so my question really comes down is, do you have any discussion about if you do just by the tensor decomposition, what's the reduction in the accuracy and how much is the effective increase by doing the partitioning?
I see. Okay, so as you're familiar with our previous paper, which is using Tensor-Train decomposition for the embedding layer in the recommendation models, we did observe that in general, like by using this low rank decomposition methods for the model training, usually we would observe accuracy degradation because of the inaccurate and low rank approximation. However, in the GNNs, so instead of the numerical features, we also have this graph topology. And that's why we propose this graph partition method here to utilize the homophily and kind of promotes the Tensor-Train decomposition to form a homophilic representation for the entire graph. And that's why we can outperform the full embedding. But without the partition, I would say that for the smaller data sets, like if we use okay, so without graph partition, it will require us to use larger TT ranks to achieve higher accuracy. That's like the general observation. For example, in papers 100M, if I remember correctly, we kind of need TT ranks at least 64 or 128 to outperform the full embedding model.
Okay.
And the accuracy of the smaller ones can be at, I would say, like 5% lower than what we reported here.
Okay, so the main reason why you are getting the accuracy is because of the graph partitioning, not because of the decomposition. So that's the main takeaway that I should have. Thank you.
Yeah.
I think I will just ask a tangential question. Have you thought about doing the graph or partitioning of even in the case of DLRM models?
I think, yes, I think the same idea can be definitely applied to the recommendation model. But the reason we didn't do that is that we couldn't interpret the meaning of the like the embedding rows in the recommendation model. Because those, right, because you know the informations are hashed and we don't know the meaning of each items or their correlation. But if given such model, given such correlation of the items in the embedding, we can do the same thing here.
Yep, that makes sense. Thank you.
Mm-hmm. And any other questions?
So what does the homophilic means here?
Sorry, what's the, could you repeat the question?
Oh, just an English term. Yeah, homophilic node.
Oh,
what does it mean here?
So homophilic means that it's a property of the graph. So it means the like the topologically closer nodes tend to share like a similar representation and labels. Like for example, in the, say, a friendship graph, the friends tend to say prefer the same kind of music or same kind of food. So when we try to predict what they like, it's like very likely those, if like those group of friends will have the same preference, therefore like the same labels. So that's the meaning of the homophily.
So that is to reduce the number of the you mean so they can share the same weights, right? Same embedding.
I wouldn't really conclude that they can share the same embedding, but intuitively we want to represent them using a similar embedding because they with some probability they will have the same like the same representation or the same property, but they might still differ, right? We cannot really say if the two nodes are connected, they definitely will have the same label. So therefore, like in our embedding, we still want to guarantee that each node has its unique representation without putting a strong assumption on how similar the nodes are.
Yeah, so why we need to train here? I mean, why we need to what is the loss function for the training?
In this model, you can, to compare with our work, you can find all the codes on the DGL example, like for the OGB dataset. So we used the same label, we used the same model and the same hyperparameters than what's provided by the DGL repository. And the only difference is that instead of using the original node features provided by the datasets, we get rid of the features and only train the model based on the graph topology.
Oh, I see. Thank you.
No problem.
Any other questions, folks? No? Well, thank you so much, Chunxing, for your presentation. And we certainly hope everyone will have a great, remaining of the summer. And I guess I'll see everyone next time. I think it's sometimes in October. We'll send out the invitation to everyone. And again, once again, thank you all for attending this. And we will have the recording available as soon as probably in a couple of hours or so. And if Chunxing and also Yiyue, if you could just post your slides on Slack channel, that would be great. And then I'll put the videos up on YouTube as soon as I get them encoded. Okay, all right. Thanks, everyone. Have a good rest of the evening. Bye.
Thank you.